So my name is Michael Jennings. I'm a high-performance computing sysadmin at Los Alamos National Laboratory. Before that, I spent almost a decade at Lawrence Berkeley National Lab just across the bay in the high-performance computing services group there. For those who might have seen the schedule a few weeks ago, I am not Reed Pridorsky. He's the author of Charliecloud. He is in the process of adopting a new baby right now, so I am taking his place. Los Alamos National Lab is one of the three National Nuclear Security Administration labs, or the tri-labs, along with Lawrence Livermore and Sandia. We are responsible for the safety, security, and effectiveness of the United States nuclear stockpile. We have a long history of high-performance computing starting back in the early 50s. A number of firsts to our credit, including the first vector computer, the first #1 on the top 500 list. And more recently, if you're in high-performance computing, you've probably heard the term burst buffer. That was also created at Los Alamos National Lab by our current HPC division leader, Gary Greider. So for a long time, HPC has been very, very good at one thing in particular, and that's building systems that run MPI, Message Passing Interface. Those are very scalable parallel applications, often tightly coupled applications. You're probably familiar with the Google algorithm of MapReduce. So these are the exact opposite of MapReduce. What we like to call embarrassingly parallel applications work very well in the MapReduce algorithm, where you can divide and conquer, and each part of the problem set is independent of each other. So if you think about a big search application, you can split the internet into hundreds or thousands of little chunks and search each individual chunk independently. Our applications are more like a climate model, where you have to break up an area of geography into a three-dimensional grid. And each grid piece has to communicate with all of the other grid pieces to pass things back and forth, like clouds or rain or wind. And so you can't simply divide and conquer these large-scale parallel applications that have been the bread and butter of high-performance computing for a long time. But as time moves on, so does the industry. And recently, we've started encountering problems where our scientists are coming to us with these massive stacks of, for example, Python scripts. Anybody who's written Python has probably used a dozen or 24 different modules to write their code. And where traditionally we have based our high-performance computing systems on things like Red Hat Enterprise or SUSE Enterprise, the typical use case today is more centered around Ubuntu, because pretty much everything ever written has been packaged by somebody somewhere for Debian or Ubuntu. And it's a whole lot easier for a scientist, a developer who's trying to get science done, to just do apt-get install or pip install and move on, rather than trying to package all of these different Python modules into RPMs that they can install. And so they're coming to us saying, I want to run my code on this high-performance system, but I don't want to have to go and rebuild all of my dependencies. I don't want to have to go and package all of my Python modules or my Java modules, or for the especially old among us, Perl modules. We also have extremely limited time. there are always more projects than we in the NNSA and the Office of Science have time and capacity for on the systems. And so we have to figure out a way to allow scientists to do science in this new world of modular, complicated software stacks without requiring them to do all the work. So the solution to this is to allow our scientists to bring their own environment. There are a lot of different acronyms and terms that have come into common use to describe this. We use the term user-defined software stacks. Other centers might say user-defined images or bring your own environment. They're all talking about the same thing. We need to be able to couple the application that our users want to run with the environment that it's going to run in. Now, every now and then, you'll get a rare bird where the application actually knows how to build itself into a static executable. That's the old-fashioned way of bringing your own environment, because all the libraries that you need are linked in. Almost no software today does things that way, and even if you do build statically, if you try to link in static libc, there are a number of calls that if you have any of those in your program, it's going to give you a warning that you still need that libc at runtime in order for it to actually work. So it's getting more and more difficult, almost impossible, to link things statically in the modern world. So one of the options that we have to offer our users is we tell them to compile things themselves. And unfortunately, that puts the entire burden on our users. A lot of our users aren't the people who wrote the application. They've been handed this pile of things that their professor or the lead scientist, what we call the PI, the principal investigator, they're getting handed this thing and they say, go run this on a system. They don't know that code. They don't know how it's built. They don't really know a whole lot about it, but they're expected to be able to build it up and make it work. And if they spend all of their time trying to build this application, then they're never going to get any science done. It's also very difficult to update. If you have to build an entire software stack manually, every time there's a new release of one of your base libraries, you have to start all over again. So this isn't portable, it's not practical, lots of possibilities for error, and it's not fair to expect our scientists to do all of this stuff. And besides, it's 2017. This is the way we did things in the 90s. There's also something that we use called an environment manager. There are a number of different terms for this as well, but the basic concept is that it wraps all of these types of requirements into a common format that you can describe. If you've ever used environment modules, this is an environment manager. Typically what it does is it will add variables to your environment. It'll change your path. It'll change your LD library path, and so forth, so that things that weren't accessible to your command line or your compiler before are now in your environment, and you can just use them and they just kind of work. The downside to this is for every single dependency that you have, you get into a combinatorics problem. We have a number of different compilers that we use. Obviously, everyone uses GCC, but we also have an Intel compiler. There's a PGI compiler. So that's 3 right there. Then for every version of OpenMPI we have, or other MPIs, there's OpenMPI, there's Impitch, there's MVAPitch, there's Cray MPI, there's Intel MPI. So there's 5 of those times 3 compilers. That's 15 different combinations that we have to support, and we've only done 2 steps of the process already. So you can see where this is going. Now, if you have to go this route, there are actually some options that make it less painful. Easy Build and SPAC are common tools in the HPC community. Both of them are maintained by existing HPC centers. SPAC is from Lawrence Livermore, just across the bay, and Easy Build is from, I believe it's Ghent in Belgium. There are also Anaconda, if you've ever heard of, used to be Continuum Analytics. Now they actually call themselves Anaconda. If you've done a lot of Python, you've probably heard of the Anaconda distribution. You can download their pre-built binaries and Python stack from their website. Something called NixOS allows you to prescriptively define an entire operating system using a single config file. And you can get Nix to install in your home directory instead of on the system. So you can use that to build up an environment for yourself. But none of those is really an optimal solution for what we're trying to accomplish. There's got to be a better way than spending all of your time building software. Apologies to anyone running Gentoo. Another possibility is virtualization, VMs. This is currently the solution of choice for a lot of applications out there. If you live in the web app world, you probably do a lot of stuff with VMs. And so it might seem like VMs are the perfect solution to this problem. Unfortunately, in the high-performance computing world, there are a few barriers to using virtualization for what we do. The big one is always performance. Anytime you are emulating something instead of running on the actual hardware, you're going to lose some performance. There's solutions to that, like paravirtualization, but there you're trading performance for security. Anytime you're running on the actual hardware, you lose some isolation. We also use some technologies that you might not have heard of if you've never dealt with high-performance computing. InfiniBand being a big one. InfiniBand is the most common high-speed, low-latency network technology that we use. And most virtualization platforms don't give you direct access to the InfiniBand network. And if you don't have direct access to the high-speed network, it's not as high-speed as it was before. GPUs are another complicating factor. So virtualization, while it works great for the cloud case, for what I mentioned before as embarrassingly parallel technologies, divide and conquer type problems, it doesn't really work for high-performance computing. There are a lot of people who would love to turn HPC into the cloud, but that's not the right answer for the problems that we're facing. So option number 4 is containers. Containers are relatively new in terms of the history of IT and the history of Unix. They've actually been around in some form or another for a number of years, but the current incarnation of them is relatively new. They give you not all of the flexibility in the world, but enough flexibility to provide a customized environment to a particular application. You don't get total isolation, but you get enough isolation to separate the application from the underlying host OS. The only portion that's shared between the container and the host is the kernel. And from a security perspective, if your kernel is compromised, you're already toast. Containers in general are extremely simple and easy to use. Most people who are coming out of college nowadays have had at least some exposure to container technology, whether it's Docker or LXC or OpenVZ or Linux vServer, there's been some sort of familiarity with running containers. And containers offer you bare metal or darn close to bare metal performance. Now, there are still some disadvantages, some challenges that we have to face. In order to do this right, you need a fairly recent kernel. If your center is still running an older distribution like RHEL 6, you're going to need a little help in order to run a proper container. And there are occasionally going to be some growing pains. The technologies that we're using have just started exposing some areas of the kernel to unprivileged users that used to not be exposed. And so there's going to be a little bit of churn before we get everything cleaned up. And one of the big challenges for HPC in particular with containers is it's very rare still to find somebody in the high-performance computing world who has true expertise in containers. A lot of people are still struggling to get the facts on what containers really are and how they work and how they function. And unfortunately, there's been a lot of misinformation, a lot of bad claims that have been propagating around the HPC community, some of it actually intentional, I'm sad to say. But ultimately, when we look at the different options that we have, containers have a lot to offer us. And so that's the road that we at LANL have decided to go down for solving this problem. Now, what are containers? There have been a number of talks so far at this conference about containers, and I don't think I've heard a single two speakers say the exact same thing about what a container is. So this is our definition. There are a lot of different takes, and they all have their relative strengths and weaknesses. But this, when we're talking about containers, this is what we're talking about. We're centering around the concept of Linux kernel namespaces. And I'll talk more in detail about that in a minute. But namespaces are a kernel technology that allow us to isolate and encapsulate an application or a suite of applications so that the version of the underlying computer that they see is separate and distinct from the actual host. And we can isolate them to the point where escaping out of that environment or escalating privileges beyond that environment is impossible. Now, I use quotes because theoretically, if there's a vulnerability in the kernel, nothing's impossible. But again, we all, when we're running Linux, accept that the kernel is our security boundary. If the kernel is vulnerable, all bets are off. So the key is not adding any additional unnecessary security boundaries to what we're already accepting. And containers facilitate and add to the security of the applications by allowing us to ensure the integrity of the application and the container environment that it's running in, and do content validation on the environment that we're providing to our applications using industry standard formats and workflows. So what are namespaces? Well, the answer to that question is changing on an almost daily basis. When we first started working on Charliecloud, there were only 6 types of namespace. Now there are 7. There's talks about doing 1 or 2 additional types of namespaces, but this is where we're at right now. As of kernel 3.8, there are 6 types of namespace. As of 4.6, there are 7. 6 of those are what we call privileged. That means you have to have a particular capability to create those namespaces. It's known as capsysadmin. If you're familiar with Linux kernel capabilities, it's just a way of separating out and categorizing different levels of capability. Traditionally, if you're root, you're God. But the Linux kernel has split out some of the different types of capability so that something that needs to run with certain elevated privileges need not necessarily be set UID root. For example, in RHEL 7, the ping executable, it used to be set UID root because it needed to create raw sockets. Now we can set capnet raw and capnet admin on the ping executable. It no longer needs to run as root because that's all it actually needs to work properly. Capsysadmin is the name of the Linux kernel capability that represents, we don't know where the hell else to put it, so we'll put it there. There are a lot of other capabilities, but this is kind of the dumping ground for everything they didn't want to split off. So these 6 namespaces, you have to have that particular capability to create, which typically means you're root. A mount namespace gives you a unique view of the underlying file systems. That can mean the root file system, it can mean other mount points underneath the root file system, but whatever it is, you have a unique view of the file system structure underneath you. And there are different flags you can set to determine whether or not changes in other mount namespaces affect yours and vice versa. PID namespace means you have a unique view of processes and process IDs. If you create a PID namespace, whatever creates it or spawns a subprocess to create it, that spawned process or that subprocess becomes PID1 with all of the caveats and implications that having PID1 represents. UTS namespace simply means you get your own host name and domain name. Net namespace is network resources. That's devices, that's IP addresses, it's routes, it's port numbers, it's firewall rules, all of the things associated with the TCP/IP stack. You basically get a unique view of that stack. IPC namespace separates out System 5 interprocess communication, POSIX message queues, shared memory, and so forth. And this is the relatively new one. C-group namespace means you get a unique view of the C-group hierarchy. So slash in your C-group FS won't necessarily be slash in anyone else's C-group FS. And then there's one namespace that's particularly unique. The user namespace means that you get a private view of UID and GID information, so numeric identifiers for users and groups. Now this one's unique because you can create it as an unprivileged user. That means you don't need capsysadmin to do it. And the real bonus is that if you create a user namespace as an unprivileged user, then you can create all of the other ones as well. There's one caveat, and it's unique to Red Hat. If you're running Red Hat 7.4, you can still do this, but there's a kernel parameter that you have to pass on the command line. We've asked Red Hat on multiple occasions why, because nobody else has this restriction. I won't say they were evasive, but they were evasive. Everybody else, Ubuntu, SUSE, the latest SLES 12 SP2 has a recent enough kernel. You can do this. Ubuntu, Debian, basically all of the others who have a modern kernel, you can create a user namespace and then create all of the others with no trouble. Red Hat, you just have to flip one little bit on the kernel command line. Namespaces have an extremely simple and straightforward API. There's only 3 system calls involved. You've got unshare, which takes an existing process and puts it into one or more new namespaces. You've got clone, which creates a new process or a new thread and puts it into namespaces. And then setNS you can use to join an existing process into other existing namespaces that were already created. If you want to learn more about namespaces and dig a little deeper than what I have time to go into, I strongly recommend that series of articles that I linked to at the bottom from Linux Weekly News. It goes into great detail, has a lot of good information, sample programs. It's great. That's how I got started in namespaces, so I highly recommend it. The container landscape, for those who might be new to it, is vast and complicated and often hard to navigate because things are changing incredibly quickly in the world of containers. When we set out to evaluate whether or not containers were going to be the right solution for our needs, we basically broke the world of containers into essentially two major categories. One is the full-featured container systems. These are the ones that try to solve all the problems and implement all the things. Docker obviously is the de facto standard, the major example of a full-featured container system. It has a runtime, it has an image format, it has a transportation mechanism to get containers from place to place to place to place. It has security paradigms, so you've got content assurance, content addressable storage, non-repudiable signatures on containers and layers of containers, etc. So it's a complete, total solution for the container problem. Rocket, LXC, LXD are other full-featured container systems. If you're going to enter the world of containers with your own code and you want to implement a full-featured container system, there are things you have to take into account, like content addressability, validating that the contents of the container when it gets run are identical to the contents of the container when it was built. Being able to sign containers or layers of containers as the builder, the source, so that if Red Hat puts out a container for RHEL 7, that when I go to run it, I know that it was built by Red Hat and that I can trust it, that they've said this, we bless this, this is the real thing. If you don't have that, then you don't have a container system, a full-featured container system. On the flip side, there are lightweight container systems. Those are the ones that pick and choose which problems they're going to solve. And typically, they just implement a lightweight runtime. So they'll run a container with particular parameters, but they won't necessarily be able to build one, or they might not have their own format for containers or images. They just want to define how to run them. Some examples of this: runC is the standard Open Container Initiative runtime. That's what's the word I'm looking for? The reference implementation. Docker, the company Docker, contributed their runC implementation to the Open Container Initiative as the reference implementation for others to look at. There's one that's written by a member of the OCI project called CCon, which is a straight C implementation of the OCI spec. Very lightweight, no frills, just a standard implementation. NSJail was written by Google. It has some additional features, not just a plain runtime, but they don't define their own image format. They use the OCI standard. Unshare, there's a command unshare that goes along with the system call unshare. If you install a modern version of util Linux, you can just run unshare with some parameters from your command line, and you can create yourself a namespace or multiple namespaces. So you can do a container runtime or execute your own containers in a shell script. For the systemd fans in the crowd, systemd has its own container engine called nspawn. Nspawn will create a namespace-based container managed by systemd. The advantage of this is that in a PID namespace, you need something to act like a init, and systemd is very good at acting like a init, as you might imagine. The downside is systemd expects a complete and total container. It's going to boot that container as if it were a machine, because that's what systemd does. So it's a bit heavier than simply running a shell inside some namespaces, but it's an option for those who already are running systemd and need something to manage the application. And of course, our implementation, Charliecloud. So in addition to namespaces, there are other components to Linux containers. Cgroups are a big one. Cgroups allow you to track and limit resource consumption by processes or groups of processes. Seccomp BPF, we just heard a great talk on Berkeley Packet Filter for debugging and tracing. BPF is also used to define which system calls applications or processes are allowed or are not allowed to use. Docker uses this to ensure the integrity of whatever's running inside that container so that it can't do certain things that containers shouldn't be doing. prctl is a privilege control method for the Linux kernel, and there's a flag you can set called no new privs. Once you set that flag, it can never be unset. And execve promises to never ever escalate privileges from that point forward. So set UID, set GID, they will never work again once that flag is set. And most modern container engines have the ability to set that, some by default, to prevent the possibility of escalation via setuid apps. SELinux and AppArmor. There's a bit of a religious war here, so I'll just say that both of those facilitate security within containers by defining what different executables and applications are or are not allowed to do. So let's talk security. There's a lot of misinformation, particularly in the HPC world, about what security means in the world of containers. You might hear people say, it's secure because your UID is the same inside the container as it is outside the container. And to that I say hogwash. If I handed you a setuid root copy of bash and said, it's okay if you run it as a normal user, you'll still have your UID once you run bash. So you can install it setuid root. It's perfectly safe, right? Yeah, you'd shoot me. And rightly so. Security in the world of containers isn't simply about whether or not you have root access. It's about prevention and protection. Do you have the facilities to ensure that you're running what you think you're running and to prevent escalations within the container? Things like content assurance, content addressable storage, and non-repudiable signatures are important. They're key. That's why Brandon Robinson wrote that manifesto that resulted in Rocket, resulted in the Open Containers Initiative, because Docker folks weren't paying close enough attention, he felt, to the security implications of what they were doing. And now we have content addressable storage layers in Docker containers. Now we can sign our Docker containers or the layers of Docker containers. And so we know where they're coming from and that they have the right stuff in them. So the picture has changed because people started paying attention to the parts of security that really count. If you've heard people talking about Docker being insecure because it has a root daemon, No, that's crap. Docker security is not about what UID it runs as. It's about guaranteeing that you're running the right stuff and providing you the tools and techniques to make sure that the container is doing what it's supposed to do and only what it's supposed to do. Thankfully, we're only doing a lightweight container solution, so a lot of that we get to leave to Docker and other container technologies. So why Charliecloud? So Docker itself now has a great security story, but it doesn't have a great performance story for HPC. The layering model that it uses slows down a lot of the file access and so forth. So it's not great for us. And there is the issue of if you have access to the Docker CLI, you can get root on the system. We could write an authorization plugin to fix that, but the performance aspect doesn't really make it the right choice for us. We don't want our users to have to worry about generating all of these config.json files. The run profile for an HPC user is pretty consistent. So we give them essentially a straightforward runtime that does all of the things they need it to do by default, and then they don't have to worry about it. And a simple API does not need tens of thousands of lines of code to implement for high-performance computing. Charliecloud is right around 900 lines of code compared to some of the other solutions that are out there. So this is a really quick walkthrough of Charliecloud, but I am going to attempt to, let me see if I can get this to come up to where you all can see it. There we go. All right, live demo time. So I can barely see this guy. This could be interesting. So the first thing we do is we build our container using chbuild. Now, I did this last night, so my Docker build cache is nice and populated. If I hadn't already run this, it would be going out and downloading OpenMPI and building it into my container. Once I build my container, I run docker to tar, and that will take my Docker container and it will build a tarball out of it in whatever path I tell it to. Once I have my tarball built, pedal faster, Grandpa. Once I have my tarball built, then I can convert it into a directory using chtar to dir. Once I've done the docker to tar, I don't need Docker anymore. So that's the part that I can do on my own workstation or my personal system, and then I can copy it up to the HPC resource. Tar to dir is what I would run on the HPC resource to extract my container. Then I can do my chrun. I give it the path to my container, and I probably can't type. Okay, so if I look at my OS release file, on my host, you see I'm running CentOS 7. But when I looked at OS release inside my container, it's Debian. And of course, I can also run MPI applications inside my container. Now there's some caveats with MPI. You have to make sure that your versions are in sync unless you're running 2.1 or later of OpenMPI. But you get the basic idea. Performance, that's the all-important thing. And how did we do? So with most code, the performance difference is negligible. It's in the noise. If you want more information on Charliecloud, we've got some great resources for you. There was a paper done at SC last year, and there's going to be another paper this year on Charliecloud. So if you're attending Supercomputing in Denver in a couple weeks, definitely come check out the talk. There's also going to be a container BOF at SC, so I encourage you to join us for that. There is an article in Login Magazine. If you go up, over, down, whichever, to registration, they've got stacks of sample issues of login. This is one of them. So there's an article on Charliecloud in the issue of login from earlier this year. So definitely check that out. It's got a lot of detail and samples. There's a sample run you can do with TensorFlow that I don't have time to show you, but you can go through an entire Jupyter notebook inside a container on your laptop, and it works perfectly. Documentation's online on GitHub. Source code is in github.com/hpc/charliecloud. We've got a brand new mailing list on groups.io you can join. And of course, you can email Reed, who's the author and primary benevolent dictator for life, or Tim Randles or myself as well. If you want to follow me on Twitter, I'm @Medge0. Any quick questions? We don't have a whole lot of time, about 49 seconds it looks like, but if you have questions.
Yeah, we have time for one question.
Okay, if you have any question.
You mentioned on one slide that the overlay FS was slow. Could you delve into a little bit more of the advantages and disadvantages between Docker and Charliecloud?
Specifically in terms of performance, so if you look at the OCI runtime spec, it basically wants you to have an exploded out container in a directory tree. So runC is already using that model, but Docker will go and make individual overlay FS layers for each of the layers in your container, and it'll tie them all together. And so you end up with a mount point that is a directory tree that has your container image in it. But there, for every layer that you have, there's an additional overlay FS portion. And overlay FS is an extremely simple format. It was created to be easy. It wasn't created to be performant. And so if you look at what it's actually doing, there's individual tarballs, and each file that's been removed, there's actually a new file that has whiteout on it. And so navigating through those individual layers to get to the ultimate result, especially if you've got a base OS and then a bunch of things, every line in your Docker file creates an additional layer. So the more complicated and lengthier your Docker file, the deeper your image gets, and the more layers you have to go through to get to what you're looking for. And in HPC, every nanosecond literally counts. So Charliecloud, you don't have any of that. It's just looking for a directory. It untars a single tarball into a single directory tree. And so you get native file system performance for accessing the content of your container.
All right, everybody, let's thank our speaker.